And that's begun now. Okay, thank you everybody for joining in, both from the University of Stirling in Scotland and MSU over here in Michigan, and from anywhere else. We're slowly trying to grow this little network of seminars to include as many people who are interested in our, I don't really know how to define it, it's just our sort of varying, overlapping interests that seem to keep growing outwards and expanding. So anybody who is interested in doing a seminar that sort of fits with most of the people here are welcome to do so. Just shoot me a message or Sandy a message if you're interested in hosting one of these seminars. So we've got this one today, and then next week we've got one as well with Professor Gabriella Koa, and that's going to be lots of fun. But today we have Clifford Bohm, who is a graduate student here at MSU, and I'm quoting online, so I'm hoping it's accurate here. Your advisor is Fred Dyer?
Yes.
Excellent. And Cliff's going to be doing, he's very kindly offered to do a seminar today on understanding evolved cognitive architectures with structural and information theory-based analysis. It's several topics kind of squeezed into one because I couldn't choose between the several he offered, so he offered to do them all, which is very nice. If you have any questions at any point, feel free to put it in the chat, and I will then interrupt Cliff and ask the question directly. And with that, please take it away, Cliff. Thank you.
All right. This is understanding evolved cognitive architectures with structural and information theory-based analysis. It's a mouthful. I am, in fact, a graduate student at Michigan State. I'm in the integrative biology department. I am doing theoretical work, though, so it's all computational, evolved digital evolution, evolution systems, and I'm interested generally in evolutionary theory, but also in the evolution of cognition.
Sorry, can I ask that everybody please mute their microphones if you're not taking part? I can forcibly do it, but I'd also like if everybody could do that naturally as well. Thank you.
All right, so this talk is in two parts. Part one is the comparative hybrid approach. And this is a method to compare disparate cognitive architectures. And part two is fragmentation information, which is a tool to quantify where information is stored in information-bearing systems and how information flows through such systems. So on to part one. So what do I mean by a cognitive architecture? For this talk, I mean an information processing structure. The process by which these structures are built or developed is not the focus here. So questions regarding direct versus indirect encoding or machine learned versus evolved encodings are very important, but for the moment, we're going to put them aside and just focus on the parts that make up a cognitive architecture and how these parts interact. So here I'm presenting a generic cognitive architecture. It has inputs indicated in blue, it has outputs indicated in yellow, and then it has memory indicated in green. And it has some internal process which takes the inputs and prior memory states at time t and converts them into outputs and updated memory states at time t+1. And you can think of this as thinking. And since I'm going to think of it as thinking, I'm just going to refer to these cognitive architectures as brains because it's easier to say. So here I present simplified schematics of our base, brain, and then recurrent neural network, Markov brains, and Cartesian genetic programming. And in each case, they have the same inputs, outputs, and memory, but now we've exposed their internal processes. And we can test these various different brain types on various problems and derive a classification based on the relative performance across problem domains. But that only provides a very gross comparison. And we can't really establish why different brains perform differently. So imagine if we could classify many types of brains in some high dimensional space. Here, I picked some brain types at random and placed them in some made up arrangement representing similarity. In this case, in this clarification, various types of ANNs all would cluster together. And I'm suggesting that ANNs are probably more similar to spiking neural nets than they are to, say, push GP. This classification approach would be limited, though, because we know that small changes in the description of an architecture can have a large performative difference. For example, consider two brain types with almost identical definitions, except the only difference is that one has memory and the other does not. It is likely that the brain with memory, while descriptively similar to the brain without, would perform quite differently on a wide array of tasks. So ideally, we could determine what exactly accounts for the differences. And this line of reasoning inspired the comparative hybrid approach. So here's how the comparative hybrid approach works. We start with the brain types that we wish to compare, in this case, CGP and RNN. We then consider the minimal changes to move from one brain type to another brain type. And so in this case, the minimum change to get from CGP to RNN, you need to change the operators from mathematical operators in the CGP to the sigmoid function operators in the RNN, and you need to change from this sparse wiring to fully connected wiring. But that's it. That's the only thing. The update functions still run in parallel. You could imagine this is sort of like a multi-layer structure where this is a single layer structure, but that, an RNN could be multi-layer. And the memory models for both is the same, and in both cases it's continuous value. And I just want to point out that there are major differences between these on other axes in terms of how they are constructed, either by machine learning or neuroevolution. But again, that's not our concern here. All that we're concerned is the performative differences between the resulting structures. So based on this, we can create hybrid brains. That is, brains that mix the components of more than one brain type. So out of my field of brains, let's consider CGP, Markov brains, and recurrent neural nets. So we identify three major, in the paper that I'm reviewing here, we identified three major axes of difference. There are more between these brain types. First, there are logical operators. In the CGP, we have mathematical operators. In the RNN, we have some summation and threshold and fire nodes. And then in the Markov brain, we have arbitrary logic tables. Secondly, we can talk about the connectivity. In CGPs and Markov brains, it's sparse connectivity. In the RNNs, they're fully connected. And then finally, we can talk about memory discretization. CGPs and RNN use continuous value memory, and Markov brains use discrete memory. So now we can take these three brain types and position them on a triangle where each type of brain is positioned on a corner. And then we can make a bunch of hybrids of these brains that mix their features and position them loosely within this triangle. And we end up with these types. So here, the black lines indicate single changes in definition. Solid colors represent the base types of each hybrid brain, and outlines in different colors represent that the hybrid brain borrows elements from different brain types. For example, CGP with discrete memory is simply a re-implementation of a CGP. It doesn't borrow from any other brain type. But CGP with Markov brain operators represents an actual hybrid where the CGP has been extended to use the Markov brain style logic gates. Finally, we run all the canonical forms and the hybrids. So the canonical forms are the original CGP, Markov brain, and RNN, and then all of the hybrids across a set of tasks. In this case, we use 3 tasks. So the 3 tasks that we used is indicated by A here is the NBAC task. This is a simple task where the input flows into the brain and then has to be repeated at various time steps. Every update, a new bit is delivered to the brain. The brain has to hold on to that bit and output it with a delay. B represents a path follow task. Here, the agent is tasked with following a path. The challenge being that when the agent is placed on the path, the turn symbols are randomized between one of these 3 symbols. And then finally, the block catch task. The agent is this paddle down here. They have 4 censored and a blind spot in the middle. and these blocks are dropped with a lateral movement. They're either moving left or right. So every time step they fall one and move either left to one or right one. And the agents must identify the type of the block as well as its moving direction. If it is one of the red blocks, it should be missed. And if it's one of the green blocks, it should be caught. And missing just means that it doesn't hit the paddle, and catching means that it does hit the paddle. So this is what the path follow and block catch tasks look like. So preliminary results appeared in an A-Life 2021 conference proceeding, and then we were invited to do an extended version, and the results that I'm showing here are from this extended version. Vertically, we see the three different tasks. So block catch, path follow, or sorry, N-back, path follow, and block catch. And then on each plot, the y-axis plots score where 1 is perfect score. And the x-axis lists all of the canonical and hybrid brain types. The main takeaways from this are that the primary indicators of performance are memory discretization and the logical operator type. Just to point out one case here, this is the Markov brain with non-discretized RNN gates, and it performs very similarly to canonical RNN. When we discretize the memory, it performs better. And we also see that the RNN with discretized memory performs a little bit better. The RNN with discretized memory and sparse representation performs about as well as the Markov brain with RNN. So there are certain patterns here. It's not completely conclusive, but there are definitely interesting patterns. And definitely we see trends. There's a lot more here, but I don't want to get bogged down in details. So, sorry, I want to just check the time, see if I'm talking way too fast. No, I'm doing okay. Okay. This. Okay, main takeaways, good. Okay, also, I want to say that these results should not be seen as an assessment of the quality of these brain types in terms of their effectiveness. We only implemented canonical versions. So these are like the originally published versions of these brain types to explore the comparative hybrid approach. There are many new variants of all of these brain types. And so, you know, any results here should not be seen as benchmarking, but rather as a proof of concept of this methodology. Okay. This would be a good time for questions if there were any.
I have any, if you don't mind, Cliff. I have a question, if you don't mind.
Yeah, please.
If you go back to just a quick one, if you go back to your previous slide, it was clear to me what the colors mean, the yellow, the blue.
Yeah, so yellow indicates that it's Markov brain. So the yellow line indicates that it's the Markov brain. Blue indicates that it's RNN, and then green indicates that it's CGP. And then when the boxes are colored, it means that it's a hybrid that uses some technology from another structure. So this is a Markov brain with RNN gates, so it's colored blue to indicate that the gate type comes from the RNN.
Okay, and the higher the better in your.
The higher the better, yes.
Okay.
Yes.
So in principle, this the top left, I think it's top right is the best performing. Kind of.
Right. So on this task, so this is the N-back task. And on this task, this is sort of an interesting thing where this is the task. Information has to be passed from an input through various memory states to an output. CGP has a particular advantage, which is it can wire directly from input to output. It can bypass using any internal logic. It's just part of what makes CGP CGP. And therefore, I think that actually explains why all of the hybrid types for CGP perform very well, is because they can actually evolve to just bypass the internal logic. And for N-back, that's exactly what you want. There's no information integration required.
Okay, thank you. You have very nice slides.
Thank you. Okay, so part 2 is on fragmentation information flow. So again, this whole talk is about introducing methods or exploring methods that are going to allow us to better understand in this case, evolved digital cognitive architectures. Okay, so fragmentation is a new information theoretic that follows from other previous tools such as representation and smearing. Fragmentation can be extended to allow for information flow diagrams, as I will show in some later slides. So some boilerplate text as to what fragmentation is. So technically, fragmentation is the size of the smallest subset of a system needed to predict some feature. So consider an election where a candidate must win 60% of the vote, and there are 4 districts, each of which contains the indicated percentage of the population. There is no one district with 60%, but if a candidate can win districts 2 and 3, then they would get 75% of the vote and they would win. So the fragmentation of this election system is 2, because we need to know, if we know the state of 2 and 3, we can predict, like, that if they're both true, that would tell us that this person won. But we could also determine who won if they won 1, 3, and 4. And so fragmentation is only the smallest possible predictive set, but not necessarily the causal set. So just because they won doesn't mean that they won district 2. They could have won 1, 3, and 4. So fragmentation is calculated using shared entropy, which is part of Shannon entropy. And it's a measure that quantifies how much common information exists between 2 or more random variables. So what we do with fragmentation is, given a feature, something we would wish to predict, and a list of nodes that make up some system that's doing the prediction, or we think has predictive power, we determine the power set of the node combinations. So we have that system of nodes, think a brain and maybe its memory states. And then starting with the smallest node combination, we calculate the shared entropy of each combination and the feature. And then we stop when we find a combination that predicts the feature. So yeah, and then we return the size of that combination. Okay, so we can extend fragmentation if we don't stop when we identify the smallest combination, but rather calculate the shared entropy between all node combinations and a list of features. So a fragmentation matrix is a table that shows how a list of features here along the bottom, a list of node combinations here along the bottom, the node combinations down here, predicts features along the left side. So it's node combinations along the bottom. And remember, it's the power set. So we start with the individual nodes. We ask, do any of the individual nodes predict any of the features? And then we go on to sets of 2 nodes and 3 and then 4. And I've skipped a bunch in the middle because otherwise this table wouldn't fit. And then we eventually end up with this one set that has 8 members, which is all of the elements in the system. Now, the system that we're using to make the predictions is the memory of a Markov brain that was performing NBAC. So we can see in brains A and B that all of the outputs can be accounted for by single nodes. So I have put little diamonds in the spaces that have predictive power. So output 5, which was the time minus 8 output, is perfectly predicted by the memory node 1. And t minus 5 is perfectly predicted by 3. Brains C and D, we see that the outputs, we see that there are outputs that rely on combinations of 2 or 3 nodes. So in a case here, we see that output 5 requires that we look at both memory 2 and 7. And here we have one in brain D that requires looking at 1, 3, and 8. What does that mean? It'll make a bit more sense. So instead of creating a fragmentation matrix, just using the hidden and the expected outputs, we can create a fragmentation matrix where the features are the actual outputs of the system and the updated memory. And the nodes, the predictors, are the inputs and the prior memory. So these matrices will have many, many more elements, and so they're quite large, and I'm not going to show you one, but we can use these matrices. Okay, well, with these new matrices, we're essentially asking, and this would be a new matrix quite a bit bigger than these, we're essentially asking, how do the inputs in prior memory predict the outputs in updated memory? And once we have one of these fragmentation matrices, we can convert this into an information flow diagram, which look like this, where inputs in prior memory are linked with arrows to the outputs in updated memory that they predict. And so this now shows how the data flows through the brains. In the case of this A brain here, we have a very simple solution. Data flows from the input through hidden and periodically to outputs as needed. Nothing interesting happening here. We can see that the input flows to M4 and M4 flows to output 1. And if we look here, we can see that output 1 is in fact predicted by memory 4. So this is the correlation between the fragmentation matrix of the expected outputs and the memory states and the fragmentation, the flow diagram. In the flow diagram for D, we can see that M6 is dependent on memory 1, 3, and 8, which is exactly what's indicated here. So these, again, in order to generate the flow diagrams, I must also include not just the memory, but also the inputs and outputs. But essentially, hopefully you can see how these things link up. It's interesting here to point out that we can see encryption. So in B here, we can see that M3, I should say, the numbers along these arrows indicate the percent of prediction by the upstream node. So M1 is 100% predicted by input 1. But at M3, we see that it has 2 inputs, but both inputs provide 0 predictive power. This is actually an encryption. So the value in M4 is being encrypted with the value in M1, and then decrypted on the next time step with the new value in M5, which was the value that was in M1 on the prior time step. So this is a simple encryption-decryption loop. Looking more deeply into this, we know that this is an XOR. So an XOR is being performed logically between M4 and M1 to generate the value in M3, and then an XOR is being generated between M3 and M5 in order to generate M8. So this, if we look at D, we see that we have similar sorts of encryptions, but we also have like messy encryptions here. We have a 00.2 on output 3, which is just a big mess. It's like, what? I don't know exactly what this is, but there's some form of decryption happening. We even have reverse loops here. So in addition to self loops, we have reverse loops. So this brain is just unnecessarily complex. There is no, as far as we can tell, there's no evolutionary advantage. In fact, when we did an analysis of mutational robustness, these more complex brains tended to be less mutationally robust. Okay, so now I'm going to show you some information flow diagrams on the block catch task. So these are Markov brains evolved on the block catch task. These plots come in pair, showing the data flow behavior over the entire lifetime versus the data flow at the end of lifetime. Notice between A, B, and C that we're looking at a variety of complexities. Now I'm just going to look at A, make some statements about this. So this represents the simplest brain out of 200 brains that were evolved that had perfect performance on the block catch task. And we can see that the entire algorithm implemented by this brain only uses 2 of the 8 available memory nodes. So it ends up that this task is not actually that hard. We can also see that the late life behavior is entirely determined by the state of 1 memory node, this M3. So basically what happens in this algorithm is early in lifetime, the agent moves around and identifies the direction and the shape of the block, and then implements a strategy that involves either continuously moving to the left or continuously moving to the right. And that, because that decision is made at this point, in late lifetime, the agent doesn't even look at its sensors anymore. It's simply executing this very simple binary choice based on 1 hidden node. So, okay, maybe went way too fast. So some closing remarks. I am curious to know if these tools can provide fresh insights into evolved digital cognitive architectures and in time biological brains. I've started to look at ways that fragmentation and data flow change over evolutionary time, including how we can observe conservation of logical features in persistent information pathways. In the future, I would like to combine fragmentation and information flow with the comparative hybrid method to better understand how architectural differences, genetic encoding, selection methods, and mutational schema affect the ways that cognition develops under various conditions. And I would like to thank my collaborators on the information. The 2 papers that we have, Information Fragmentation Encryption and Information Flow in Complex Biological Networks. Thank you, Chris Adami, for that name. This is going to be appearing in an article of Entropy coming up, and it's on archive if anyone wants to see it. And then using the comparative hybrid approach to disentangle the role of substrate choice on the evolution of cognition, Acacia is responsible for that title. And this will be appearing in a special issue of the A-Life Journal soon as well. And also thanks to Beacon and Michigan State University and ICER for all the compute hours. And that's it.
Excellent. Thank you so much, Cliff. That was really fascinating. And honestly, I think your work is very it's very challenging. Like, that must have been a really difficult set of topics to get into. To me, it seems like a very abstract concept I wouldn't know how to get my teeth into. And that's my main question for you, if you don't mind me jumping ahead of anybody else.
No, of course not. No, so I was in, so my background is computer animation. I spent almost 20 years working in industry, first on commercials and then on film effects, and kind of had enough of that and decided that I would do something else. And then I ended up here. And when I moved here, I moved here because I went to college with Charles Ofria. And when I got here, I wasn't sure if I was going to go into art or I was going to go into academia. And I started hanging out with the Ofria lab people and the Adami lab people and Aaron Hinsa and his lab. And then Aaron hired me to develop a piece of software called MABE, which is, it's a modular agent-based evolver. So basically, he wanted something like Avita, but for Markov Brains. So something where we could swap out the worlds more easily rather than starting with a sort of janky piece of code every time. And I said, well, wait a minute, if we're doing this, why don't we allow swapping out brains as well? And even the genome model. And then that put me on this path of starting to think about creating various hybrids and how to talk about comparing them and what actually makes these substrates different. And sort of, so I've come into this thing completely the wrong way. I've come into it from a non-academic approach and just asking all the questions that I shouldn't be asking because I didn't learn it right.
I have to disagree. I don't think there's a such thing as entering the wrong way. I think you come in with a different set of experience, which is valuable. because that's something that we often lack in academia. People often go straight into it without any experience of the external world or industry or anything like that. So you're bringing in skills that otherwise don't exist here, and that's a very good thing.
Oh, I appreciate that.
I do have one more final question. It's kind of
Sure.
Similar to the previous one. How difficult was it to distill the features of like the individual digital cognitive architectures and then implement them into each other? I mean, actually, again, it's that sort of abstract consideration of what makes each architecture unique and what are the features and how can they be extracted? How tough was that to actually do?
Yeah, so the answer is easy now, hard early, because now I only think this way. But early on, it wasn't obvious at all. But now it's like you're combining a memory model with some logical operators, with some connectivity, with a mutational schema, with a selection method, with an encoding of a problem, et cetera, et cetera, et cetera. And you bring all these pieces together, and that makes your evolutionary system. But you could go in and change any part, and then it's a new evolutionary system. And so if you think about, I mean, with developing MABE, it forced me to think modularly in terms of being able to swap the brains and the tasks. And so this just progressed one level deeper to say, okay, well, let me so I did have to rebuild. I had to write a new version of CGP because if you want to integrate the recurrent neural net gates, you can't use the 2-input operator genome. You have to allow for more inputs. So you have to basically leave space in the genome for potentially more inputs. Of course, it's going to have encoding effects, right? And so like that would have to be disentangled in the future as well. But does that answer that question?
Very much so. It's honestly a very, very interesting topic. And so I won't hog any further questions from me. Does anybody else have any questions they'd like to raise to Cliff?
Question. What's the state of implementation if we wanted to actually poke around in code of one thing that can be defined as another thing?
What is the state
in terms of these architectures? So that you have CGP, and you proposed a way that it could be turned into an RNN?
Sure. So I have the implementations that with the paper, we're shipping a replication GitHub site that includes all the code. I don't want to say it would be trivial to extend the Markov Brains or CGP or any of the architectures, but it's not rocket science. Basically, with I think again, it's sort of a confluence of being in the right place at the right time. With Markov Brains, traditionally Markov Brains had either deterministic or probabilistic logic gates. So these took binary inputs and then they performed, they basically had a lookup table and then they would spit out an output. But the critical thing here was it was either deterministic or probabilistic. And so initially it was already like there's a switch where you have more than one type of gate sitting in this brain type. And then from there, like it was very obvious for me to say, well, wait a minute, why? Actually, before me even, I mean, I think when I already came in, Aaron and Jory were already doing this. You can put in a counting gate. You know that, well, these 3 gates implement counting. So since we know that the brain can evolve counting, let's give it a counting gate, or let's give it a spiking neuron gate. And then that got me thinking in terms of how to build modularly. Now, CGP also does the modular thing, but it's kind of fixed with the 2-input operator. So it's, it's operator input, input, operator input, input. And so all you need to do to get away from that is say, okay, well, let me re-implement CGP where I'm not restricted to this genomic model. So I would say if one wanted to do this themselves, it's not that big a deal. If one wanted to pick up on the code that I've already developed, it's available.
Does that answer your question, Jory?
Very much, thank you.
I have a question, but I don't know if someone else has. I already asked one, so well, it's a couple, but the first one is more like a comment. When in the first part of your talk, when you talked about classifying architectures, I was wondering that, I mean, some of the systems that you mentioned, for example, NEAT or Cartesian genetic programming, they involve both representation or an architecture or an encoding, but also involve an algorithm, a learning algorithm, etc. So I wonder whether your classification should separate both, or, I mean, one is the encoding or representation and the other is the learning or the algorithms, if that will make your classification easier. Because I imagine that, okay, so evolution is something that can be applied maybe in general to many search spaces or encodings, but some other methods are more specific of the architecture. So I want to see your views on that.
I completely agree. I on that slide where I list all the brain types, there's an asterisk sitting next to NEAT, because NEAT is not just a brain structure. And in fact, it's been very interesting because I've had conversations. You know, Charles Ofria developed Avita. Charles Ofria and Titus Brown and Chris Adami developed Avita. And when I've talked with Charles about Avita, I've said, look, there are two ways you can think about Avita. You can think about Avita as a circular genome that lists the instructions directly, and then it's a direct encoding. Or you can think of it as simply a list of instructions, and I don't know how I got them. Right? I could encode a genome where there are start codons, and each start codon is followed by an instruction and then some modifiers on the instruction. And that I could also build an Avidian. So in this presentation of the comparative hybrid approach, we're really just interested in the resulting structures. So if somebody implemented NEAT so that it gave you a recurrent neural net that was indistinguishable from a recurrent neural net that was generated by, let's say, backprop, then as far as this particular paper is concerned, it doesn't care. It doesn't care how we got there. Now, I absolutely agree that how we got there is critical. And so I think that implementing NEAT to generate simple recurrent neural nets, and also generating simple neural nets with the same architectural structure using something like backprop, and then also using neural evolution, and then looking at how that developmental process, random, let's say an indirect encoding neural evolution, looking at how the process of generation results in changes to either performance and or how information flows, how the algorithms are implemented. I think that is, to me, this is, in my opinion, the most interesting, maybe I'm biased. I don't want to oversell it, but maybe to me, it's the most probable path to actually getting some answers to why these different systems perform differently.
Okay, thank you. The other one is a quick one, less philosophical. I was a bit curious about your slide when you said you were comparing two architectures or two neural networks, and you were saying one is the lifetime and the other one is the late lifetime. So that means that you have a system that the agents continue to evolve, or can you describe the context of what you mean by full lifetime? Mm-hmm.
In this context, these brains were evolved for 20,000 generations, and we're looking at the end of evolution. But when we look at pull up that slide again. Am I sharing this screen?
We can currently see
I am
your
sharing.
task
Okay.
manager.
Okay. All right. There we go. Oh, I thought I had stopped sharing. Okay, my bad. All right. So let me minimize this, and let's go back. See, these are the slides I was gonna make you sit through, and you didn't want that. So you were asking about. Okay. So here's the block catch task. So we consider a lifetime in both of these tasks a single pass on the task. So in the path follow task, a lifetime would be the agent is positioned on the starting position and the lifetime ends when they get to the end position. In block catch, a lifetime starts when the block is positioned at the top of the world and it ends when it reaches the bottom. So full lifetime is we collect the information from the inputs, the memory, and the outputs over the entire lifetime. And late lifetime is the last 25%. So from about here down, we only collect that data, but we collect it across all of these trials. So we give a trial right there. Each agent is experiencing multiple lifetimes. You could think of it as tests, right? So you could think of it as full test and late in test. And so what this is saying is basically that simple brain, it was doing all of its classification of the block type, whether it should catch or miss it, before the block got to this level. Once it got to this level, it had encoded it locally, and it now was just executing an algorithm. If we look at these path follow brains, since they have to identify which symbols mean left and right. Sorry about that, I should have made that bigger. Since they have to identify which symbols mean left and right, these brains tend to learn that very early, right? They maybe make a mistake early on because they have to figure out left and right. But once they've done that, they know it. And so these brains also, like, they localize the information and then they just utilize it. Does that make sense?
So basically, you're saying that the lifetime of the agent, he has a different brain at the beginning and at the end? Or?
No, I'm saying that the way that information flows through the brain is different.
Okay.
So imagine if you wanted to learn how to play soccer. When you first go out, you don't know how to kick the ball, you don't know how scoring works, and you have to pay a lot of attention. You're paying a lot of attention to all of your inputs. You're paying a lot of attention to how the game mechanic works. But once you've been playing later in your lifetime, you've had experience. Now you know how to kick the ball. You don't think about kicking the ball. And at a certain point, you almost get this Zen sort of like, I'm just playing the game. It's all on autopilot. And so this is a much simpler version of that. But basically, the idea is that early in the lifetime, whether it's on this path follow task or the block catch task, the agents don't know either what the turn symbols are or what the type of block is. And so they have to go through a period of discovery where they discover what kind of world am I in. But once they know this, then they can localize this information in memory, and then they can just implement their algorithm.
Okay, thank you very much, Cliff. Thank you.
That's a very hand wavy. I mean, human brains are not these things at all. So I don't want to conflate the two things, but in terms of understanding what it's about.
Cliff, I have a question.
Oh, go ahead, Wolfgang.
My question is, for your information flow analysis, do you need to discretize the states of whatever you have, neurons or?
Yeah, and you can't have too many. So if I get above about 20 nodes, I'm going to be in trouble. Just process. Now, I can do certain things. I can. I'll answer the question you didn't ask first. So in terms of size, I can discount sets of intermediate size. So I have to create the power set, and that is where the problem comes in. But if I say I'm only going to look at the sets of size 1, 2, 3, and 4, and then, you know, n minus 1, n minus 2, n minus 3, that's actually not so bad. And a lot of times, like if you're looking at, if it requires more than 4 nodes to predict a downstream state, then you could just say, well, that's complicated, right? Like it's not going to be clear what the information flow is anyway. To answer your question about discretization. So if I want perfect information flow, then I need perfect discretization. So if I have an actual continuous value structure, I'm going to be in trouble. So like when I've done information flow on RNN structures, I've discretized their memory. But I can do different discretizations. So I can do average discretizations, or I can do median discretizations. Also, I can have a system where the memory states aren't continuous, but they're also not binary. So I could say, oh, I'll make an RNN where the states can be -1, -0.5, 0, 0.5, or 1. And then that's 5 states. And then since that's discretizable, I can work with it. But if you start to discretize and you're not careful, you'll lose information, and then it becomes hard to make your predictions.
Okay, thanks.
So I would say this is a tool for I would say for a lot of real world problems, it would be hard to deploy this without, quantum computer level technology. But in terms of the stuff I'm interested in, which is understanding how evolution works and maybe being able to predict what will make useful models in the future, I think this could be a good tool.
Thanks.
Okay, it's a good thing your talk was a little bit shorter, Cliff, because I think we've had a lot of interest in the questions, which has been great. Okay, with that, I do really want to thank you again, Cliff. That was an excellent presentation, and I'd like to echo Professor Okoa's comments. Your slides and visualizations truly were excellent, so much appreciated.
Thank you.
This recording will be available to anybody who's interested on YouTube. So, if you want to watch it again and see any particular slides, you can find it. We'll be posting it on Twitter and such, so you can find the link there, and I know Slack and such. Next week, we have Professor Okoa doing a presentation as well. So be sure to tune into that, and that'll be good fun. With that, thank you all for showing up today. Excellent. A number of people came along to listen to Cliff talk, and that was much appreciated. So with that, we'll thank you again, Cliff, and thank you all for attending. We'll see you next week, hopefully.
I'll see you this afternoon.
And this afternoon, yeah.
Great. Thank you very much.
Bye.